Hey guys, welcome to my channel. In this video, I'll guide you through a simulation of a marble scenario using R to unravel the magic of the Central Limit Theorem. Let's get started. So imagine that you have a bag filled with red and blue marbles. How would you guess the proportion of red ones without going through every single marble? So you might think, what if I grab a handful and calculate the percentage of red ones from there? Bingo! This sampling mindset is a cornerstone of the Central Limit Theorem. Let's dive into it. To start, we need to get our population data set. I'll use Tidyverse, which is a very useful, awesome R package, and I've created some helper function to generate samples repeatedly and visualize the data points. And I defined the red and the blue marbles here. So we will have 1,000 marbles where 64% of them are red. I'm using the simple sample function to generate our population data set. Let's put our sampling function to work. Here is the sample we get if we set the sample size to 10 and we draw once. So we have two columns. One is sample number and the other one is sample value. So the one in the sample number means that this is our very first sample, okay? And the one in the sample value means this is a red marble. 0 means a blue one, okay? So tiling it up, and we will have 50% of the red marbles. So if this sample were a perfect mini version of the whole bag, so we'd estimate that 50% of all marbles in the bag are red. But remember that it is only just one sample, okay? So while it gives us a snapshot, it might not perfectly capture the true proportion of our massive collection of marbles. So what if we take more samples and to verify this 50% and double check? So let's say we draw 10 marbles for 100 more times, okay? We'll get the samples here and we'll calculate the sample means. And we have this data frame. So here it means that the first sample we have 50% of red marbles, and the second sample we have 70% of red marbles, and so on. So clearly there's variability between our sample proportions, right? And how can we measure this variability? So remember that the standard deviation measures the dispersion of the data points. So when we talk about the standard deviation between samples, we refer to it as the standard error. And this matrix tells us about how much the sample means fluctuate around the population mean. And for this 100 samples here, the standard error for the sample means is 0.17. And let's put this into visuals. Okay, so here's the plot. On the top part of the plot, we have the samples. And these are, so for each row means one sample, okay? So these are the blue marbles and these are the red marbles, okay? And the orange dots means that percentages of the red marbles, okay? And the bottom part is a histogram, okay? So as we can see that the sample means are around the true population mean, okay? And some are lower and some are higher. And we have some extreme values like 0.1 and some are near 1. But notice how spread out they are. It suggests that drawing just 10 marbles at a time might not give us the best representation. So what if we bump up the sample size? Let's say 20. Okay, so we get the sample, we get the samples and we'll calculate the sample means. So the standard error for this sample means is 0.1. So it's getting better, right? It's better than 0.17. Let's check the visuals. So by doubling our sample size to 20, we have more sample means between 0.5 and 0.8. Okay, we don't have any sample means below 0.1. And we don't have any sample means near 1.0. Okay, so how about increase the sample size to 50? With a leap to 50, the standard error shrinks further from 0.1 to 0.07. which is a 30% drop. When we look at the visual, we see a tight cluster between 0.5 and 0.8. So curious about the sample of 100 marbles? Let's take the plunge. So with 100 marbles, our standard deviation decreased to 0.05. And our sample means, when we look at this histogram, snugly fit between 0.5 and 0.8. And our density plot is more bell-shaped. So that's unravel the magic behind the central limit theorem. So the central limit theorem states that as the sample size increases, typically when it's greater than 30, the distribution of the sample means approaches a normal distribution. Okay, so you may wonder, does it apply to any distribution? So what if we have a very skewed data set? So here we've used a log normal distribution to mimic a real world salary data, which tends to be skewed to the right because there's no upper limit on high salaries, right? So when you look at that, we calculate the sample mean, which is 48,000. So when we sample and plot, something cool happens, okay? All sample means hover around the true population mean. And all the sample means are between 1,000 and 100,000. Okay, so and when you look at the density plot, it is still a bell curve, which means that the central limit theorem still holds. So here are the key insights from the central limit theorem. Sample means cluster around the population mean, some higher and while others are lower. And large sample sizes decrease variability. So when we increase the sample size from 10 to 100, when you look at the histogram, when we increase the sample size from 10 to 100, the sample means are getting more tightly around the population mean. Okay, and the distribution of the sample means becomes more normal as size increases. So when you look at the density plot, it's getting closer and closer to a bell-shaped, aligning with the normal distribution. And it works for any population distribution. Whether skewed, uniform, or bimodal, the sample means will still approximate a normal distribution if the sample size is large enough. So now, how would you estimate the red marble proportion in the back? So we take 100 marbles and we calculate the percentage, which is 60% for in this case. And then one question arises. So when you use the sample mean to estimate the population mean, so how confident are we about the estimation? And how can we quantify our level of certainty? So this brings us to the idea of confidence intervals, which we'll dive into in the next video. Stay tuned. If you find this video helpful, please like and subscribe. Thank you for watching.